All right, in the last video we talked about the shapes of orbitals and the effect of where that comes from based off the quantum numbers and all of that stuff. Okay, in this video when you start talking about electron configurations, which is literally applying those concepts to atoms. So basically if you have an atom and it has 20 electrons in it, we want to know where are all 20 electrons. This is a simplified version it's a streamlined version of quantum numbers. Okay, so electron configurations, they describe the distribution of electrons in an atom. Okay, they use something called the Spdf notation. Okay, I'm just going to draw an example and kind of point out a few things about what it means. You don't get all 4 quantum numbers, you only kind of get the first 2, maybe 3 out of this one, but that's okay. So it looks kind of like this. So in terms of labeling a few things here, this 1 in the front is your N value. This is your L value, and remember that L's there's numbers for them, but we also substituted them for letters, so it's the different types of orbitals. And then this just tells us how many electrons are in that orbital. So we definitely get the N value, we definitely get the the L value. The M sub L value does determine how many electrons each of these can hold. It turns out that each orbital type can hold 2 electrons. So if you have an S orbital, this can hold up to 2 electrons. A P orbital can hold up to 6. A D orbital can hold up to 10. And an F orbital can hold up to 14. Essentially, those M sub L values, the different orientations, each orientation can hold up to 2 electrons as long as they have opposite spins, different M sub S values. So for an S, this can hold up to 2, so this one is maxed out. For a P orbital, it can actually hold up to 6, D orbitals can hold up to 10, and Fs can hold up to 14. Fs don't come up all that often, but it's probably still good to know. Okay. This is the most common way to do electron configurations, and we are going to do a lot of this. But there is another slightly more detailed version of this called orbital diagrams. It's similar, it's related. It's essentially just electron configurations with more details. So for orbital diagrams, what you would do is it's the same idea, but we need a box to represent each possible orientation. So basically this is one orientation. This has 3 orientations. We saw this in the last video, but I'm going to rewrite it here just to make sure it's in your notes. 5 orientations. And this would be 7 orientations. Okay, so essentially these are electron configurations with boxes to represent the different orientations. And arrows to represent the M sub S values. So here's an example. Okay, so let's say we had, I don't know, I'm just gonna make something up here. What we could find for something up here, this version would be a 2p4. So if n equals 2, L could equal 1, which is a p orbital, and that can hold up to 6, so 4 is not an unrealistic answer. This is the electron configuration. The orbital diagram equivalent, what we would do is we would have 3 orientations, so we get 3 boxes. They are all connected. I don't care how perfect your boxes look as long as I can see that there are 3 of them. This is a 2p orbital, so we're still going to write that underneath. And then the way it works is each of these, there's a 4, each of these it needs to be represented by an arrow. The way this works is each box gets an up arrow before any of them gets a down arrow, before any of them gets paired up. So 1, 2, 3, 4. This is why we use the little single-sided arrows, so we can fit 2 in a box without overlapping them. Okay, this is the orbital diagram version of the exact same piece of information. Okay, now we technically can get, for each of these individual electrons, we could get all 4 quantum numbers out of this. It's a little more complicated than just the n and the l value. That part's the same. So that's your n, that's your l. The m sub l, we said that n is 2, so l can be 0 or 1. In this case, it is 1. So m sub l can be anywhere between -1, 0, or +1. So that's what these boxes represent. -1, 0, +1. And so if we looked at any individual electron, so let's say we picked this one. Okay. The n value equals 2, the l value equals 1. This told us that. M sub l equals +1, and the m sub s value is either +1/2 or -1/2, which I guess I could write up here. The up arrow means +1/2. So this individual electron has all 4 quantum numbers defined by the orbital diagrams. We just use arrows and boxes to represent it all instead of having to deal with all the numbers every time. Okay. So for any, I guess I forgot to write this down here, for any situation, the m sub s, the spin values are either +1/2 or -1/2. Okay. So these tell us the same thing. This is just significantly more detail. Okay. If I asked for the orbital diagram, I only need the part that's in black. The blue is me trying to describe it. The red is me picking an individual electron and describing all the quantum numbers. Okay. So I'm mostly going to focus on electron configurations, but we're also going to kind of do some orbital diagrams at the same time because they're kind of the exact same concept. One is just more detailed than the other. So whenever you have an atom with a bunch of electrons, well, anything more than one, basically, the way it works is it fills from the lowest energy to the highest energy. Okay, so the rules here kind of work like this. Electrons occupy the lowest energy orbitals first. Now, this leads to the question of how do we know which ones are the lowest energy? That's actually slightly complicated, but that's okay. We'll get to it in a second. The second rule is that no 2 electrons can have all 4 of the same quantum numbers. They can have like 3 of the 4 of the same, but they can't have, has to have a unique combination of 4 quantum numbers. So no 2 electrons can have the same 4 quantum numbers. Now, this is true for any individual, like if you have electrons in the same atom, this is true. If you had like 2 carbon atoms, an electron in one carbon and an electron in another could have the same 4 quantum numbers. Okay. And yeah, so we'll stick with 2 rules for right now. We'll probably throw more things on here as we go. But the idea is we need to figure out what is the order from lowest energy to highest energy. And this is probably significantly more complicated than you might expect, but that's okay. Here is the order. I don't know if I'm gonna have room for all of this. Lowest energy to highest energy. I do not need you, I don't even want you to memorize this list. I'm gonna show you how to use the periodic table to get this list here in a little bit. Okay, but here's the order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, I'm running out of room, so I guess I'll continue down this way, 4f, 5d, 6p, 7s, 5f, 6d, D, 7, P. Supposed to be a 5. Okay, so at first glance, the trend I'm going to point out here is for any n value, let's point out 3, okay? S is lower than P, which is lower than D. For 4, S is lower than P, which is lower than D, which is lower than F. Okay, so they're in order, S, P, D, F. That's the order that they fill from lowest to highest. And it almost starts out in a nice systematic form. We do 1S, then 2S, then 2P. That's the only options for 2. Then 3S, then 3P. And then for some reason the 4S jumps in between these two, and then jumps up to 3D, then 4P, then 5S jumps in, and then everything kind of gets out of order at that point. It feels like it's just kind of a jumbled mess. We will figure out how to use this sometime real soon. I'm honestly just going to show you how to do this using this method, and then I'll show you how to use the shortcut maybe in the next video. Okay, so let's just try some examples. Let's literally start with hydrogen. Hydrogen is element 1. If it doesn't have a charge, it should have 1 electron. Okay, so we start at the lowest energy. That would be 1s. This can hold up to 2 electrons, but we only need to put 1 in there. So 1s1. Pretty boring, but that's the answer. So these are electron configurations. I'm also going to draw the orbital diagrams next to it. You can do both at the same time. On a quiz or exam, I will ask for either electron configurations or orbital diagrams, so you need to know which one's which and how to do both. But essentially, the electron configurations is the standard, straightforward option. Orbital diagrams are the same thing with boxes and arrows. So an s orbital has 1 orientation, so we get 1 box. We write the 1s underneath. It has 1 electron. We get the up arrow first. They mean the same thing. This is just more detailed. Okay. I'm not going to do every element, but we're literally going to jump to the second element. Helium is element 2. It should have 2 electrons. So we still start at the beginning. We don't care what hydrogen did. We still start at 1s. This can hold up to 2 electrons, 1s2. For the boxes, an s orbital still gets 1 box, and it has 2 electrons, but the up one first and then the down one. Okay, trying to keep this on the scene here. Let's jump up to carbon. Carbon has 6 electrons. Okay, so this is 1s that can only hold up to 2. So that one's full. So now we go to the next one, which is 2s. That can hold up to 2. So now we're up to 4. The next one is 2p. This can hold up to 6, but we only need to put 2 in there because that'll give us a total of 6. For the orbital diagrams, we've got to draw all the boxes for all of these. So 1s, that has 2 electrons in it. 2s, that has 2 electrons in it. P orbitals have 3 boxes. We need to put 2 electrons in. Each of these is going to get an up arrow before any of them gets a down arrow. And we start from left and work our way over. So this would be the orbital diagram for the same thing. Okay, but literally you just kind of work your way through. Obviously, as we get towards things like Mercury, which has 80 electrons, it's gonna take us forever. We're gonna find shortcuts, we're gonna find easier ways around this, but that's okay. Let's do, I don't know, aluminum. Aluminum is element 13. So we start at 1s. That's 2. 2s2 would give us a total of 4. 2p, this can hold up to 6. We're now up to 10. We're shooting for 13. Now we jump up to 3s. That can hold up to 2. We're now up to 12. And then 3p. This can hold up to 6, but we only need to put 1 in there. Okay. I'm going to draw the boxes underneath just because I don't have room otherwise. Okay, so you'll notice this is starting to get pretty tedious. Okay, let's actually stop there. In the next video, I'll show you how to use the periodic table, which will hopefully streamline this entire process. Okay, thanks.